interface with you, right? Next week, we are actually going to see a film called The Day of Trinity, and it's about how the people who designed the atomic bomb, how they felt after the atomic bomb has been launched, right? And after today, after your name again, Guillermo's talk, right? We will also have the physicist Lyn Cominsky talking to us about the science of war and peace, particularly on drones. I mean, maybe some of the nuclear mass destruction as well. So you can actually see that we have many talks on the scientific aspect coming along, and science can actually create a situation in which that we no longer come face to face with our enemy, as in the case of drones, right? Computer, satellite technology is increasingly creating that, and these more stories, you can say besides the opposite of it. And there's also a really good beauty in the fact that he was originally a financial analyst in the war bank. He quit his job in order to start his journey. So, that's why I thought that it would be actually good to actually invite you to actually come face to face with him. And if you have any questions for him, or if you want to actually connect with him after class, please let us know, and then we will give you the address to actually make connection with him.
Good afternoon, everybody. At first, please, I'm sorry for my English, really not as good. It's another challenge that I have in my life right now, try to learn English. Well, thank you for introducing me. My name is Guillermo in Argentina with accent. And I was traveling for 4 years, 2 months and 26 days from Patagonia, the bottom of the world, and I finished it in Prudhoe Bay 1 month ago, exactly today and 1 day ago. I was in Prudhoe Bay, where was the goal of my travel. Today, Barbara invited me because she told me that you are trying to study the ideas like the war and the peace. And well, in my travel, I think that I could enjoy my travel, and I would like try to share my experience in this way. No, because in the beginning the travel was to me like a big adventure, but then little by little was becoming like in a big cool school of the life. Yes. Well, I was in really a lot of culture. I was in Argentina first, then I was in Chile, Bolivia, and in all these countries I could see different kind of people, no, and how they try to keep going their life. Yes. I'm sorry if somebody don't understand something. Please let me know, and I can repeat again. Well, I told you that I was in a lot of countries, and I could see how the people try to live life in different way. Yes, but for me it was something weird that the people try to live with. It doesn't matter what kind of culture is or what kind of behavior they have. Really, they try to get all the time the same stuff. Yes, and I could see that. You see, I have to do something writing because in English it's hard. I could see how the people that enjoy the work that they do, they can have like a better life. Yes, why? Because to me, my travel was like in the beginning was like a challenge, But then, to do that, I was traveling without sponsor and without any economic support. Yes. Why I had the idea to do that? Because I saw that in my old job, really, the award of my job was all when the month finished. The award was the salary, yes, and I feel that I was losing my time in my office because really I like my old job, but the award of my job was the salary, yes. But to do that, all my life I like riding, I don't know, do a sport, travel, know about the different culture. And with my travel, I could find the way to enjoy the activity day by day, yes. And in this way, I feel like full, yes. But in my travel, I could see that people that don't enjoy the activity that they do, they are like empty. And when you are empty, your spirit is empty. You have to get different stuff to put inside, no? Trying to put inside and to, I don't know, like tap, yes, this hole. Exactly. Thank you. What is the idea? When you are something like happy, yes, with your activity, you feel full, and you can make, I know, you can share the life in different ways, yes, because you are really, the word is pleno, ¿cómo es? Full, okay. But when you are empty, you have to do a lot of stuff, or really buy a lot of stuff, because you try to get your personality outside you, yes, and in this way you feel that the world is the scenario where where you can get the stuff to do that. And what I mean that when you are happy with your life, doing the things that you like, you feel that the world is like harmony, yes, because you are like in vibration with everything, yes. But when you don't, when you feel empty, like I was, really you feel that you have all the time to get something new to be better, yes. And for that, sometimes people that is empty feel that outside them everybody is working to make a damage to them, yes, because the ego try to get the stuff outside, and really the ego have to work inside our, yes. The idea is that our desire work inside your inside our, because in this way you can get the activity that you like. To me, for example, my travel was like every day when I was going to my bed or my sleeping bag, really. My word in the day was do that, yes, and I never wait for nothing else in my day, because I was happy because in this day I could ride, and for 4 years I was doing the same things, and I enjoyed that because it was really, you know, every day wake up and have the possibility to ride. For me, it's something beautiful. And I'm really, I don't have to, or yes, I don't have to expect at the end of the month to get my salary, yes, because every day I had my salary, yes. Let me see. I would like to share a video that I made me in San Francisco, because there I can explain something. First, this one is from Mexico.
Bueno, mi nombre es Guillermo Federico Aimar, soy de Buenos Aires, Argentina, y tengo 32 años. Partí de la Patagonia, Argentina, y voy lento pero contento con rumbo a Alaska.
El proyecto
Ushuaia,
Alaska.
¿Alaska?
No, este es el mapa de mi viaje. Hasta aquí, después de 3 años, 2 meses y casi 11 días, he recorrido unos 32.000 kilómetros, tal vez algunos más o algunos menos, pero y me restan aún unos 12.000 kilómetros más. Quería con el viaje proponerme una nueva meta, ¿sí? O sea, un aprendizaje de vida también. En realidad, cuando me propuse llegar a Alaska, no me lo propuse desde que quiero conocer Alaska. Si quería conocer Alaska, me tomaba un avión. Visité todo Argentina, Chile, Bolivia, Perú, Ecuador, Colombia, Venezuela. Luego volví a Colombia para cruzar a Panamá, Costa Rica, Nicaragua, Honduras, El Salvador, Guatemala, Belice y entré a México. Lo que más me gusta del viaje es que justamente aprendí a vivir con lo que necesito, no con lo que ambiciono. Entonces lo que noté es que el viaje me enseñó eso, a saber qué es lo que necesito para construir mi meta. Normalmente estamos acostumbrados a ver qué es lo que nos falta en la vida y tratamos de buscar lo que nos falta sin saber para qué lo queremos. De hecho, en 3 años nunca he pagado por hotel. La verdad que el 70% de mi viaje se lo debo agradecer a la gente que siempre me ha dado o brindado un lugar. Normalmente, si estoy en la ruta y no llego a un pueblo, también armo mi tienda. Bueno, este es el libro mío de viaje. La idea es que cuando me propuse hacer este viaje, pensé una forma, no quería hacer un viaje turístico de solo ir comprando cultura, sino que yo quería conocer los lugares desde cómo son. Entonces me pareció que una buena forma de conectar con los lugares era ir visitando instituciones infantiles o colegios donde uno pudiera llevar un mensaje motivador a los chicos. Lo que busca este libro es armar un canal de comunicación entre todas las culturas de América, porque en cada lugar que paro los chicos escriben sobre sus tradiciones, culturas, costumbres, no sé, forma de vivir. Para este viaje no hay una universidad, no hay un lugar donde te puedan enseñar a cómo viajar. El viaje en sí tiene la energía de tu propia personalidad y de la voluntad que vos te propongas para realizarlo. Entonces se va armando como un hilo de comunicación entre todas las culturas que voy visitando, ¿no? Todas las culturas de América, porque mi viaje es por toda América. This is the idea, no, of my travel. Why I was riding my bike, yes. But what happens when you buy a lot of stuff? Yes, this stuff start in your to be like armor. Yes, because maybe you get I don't know, a new cell phone, you get a new dress, you get a new career, maybe you go to the university, all the stuff that are around you and became like in armor. Yes, armor is yes, armor. Thank you. And what is the problem of that? That when you are living in harmony, the life is open because you are like you are really sensitive. Thank you. But when you buy a lot of stuff and your knowledge is too much, you are really closed. Why? Because you have to defend all the time your ego. Yes. What is the problem when you do that? Then you have to defend yes, all your stuff because you are your life run thanks to this armor. For that, to me, it's crazy because I feel in my travel I feel that every day I was like in war because every day I had a different challenge. Yes, but it's a war inside me. Yes, it's because I want to be better every day, but the war not is outside. Outside, the planet is like a chaos. Always the planet was in the same way, but I have to put in order myself first. Then, if I have enough time in my life to try to change something else, I would like to do that. But in the first, I have to put in order myself. But I feel that people that is empty, yes,
I feel that they saw first that outside is in disorder, and they try to change all outside them, and then to try to I don't know, transform. Exactly. Thank you. Well, and for that, to me, this is the beginning of the war, right? Yes, when really we don't know where we are going. Yes, because we want to change all kind the stuff, or when something is different to us, we want to change because it appeared like a problem with to us. Yes, because it's better try to ask that another change and not change me, because it's really hard change myself. No, it's easier to ask to another that change. This is my idea really of the war. I don't know if somebody have some question right now. Guillermo. Yeah.
Which was your favorite country that you visited?
Yes, really it's hard try to choose only one, because I told you that in my travel I was meeting people, and to me the biggest experience was with the people, not with the countries. And you can find the people that you are okay in all the countries. I can see that maybe, I know, Mexico, Colombia, Venezuela, the people is really friendly, but really you can find this kind of people in everywhere. And I think that, for example, the landscape always is something beautiful. It depends on you if you can see the beautiful of the landscape, yes? But people always have something to share with you. Good things and bad things. And also depend of you if you can see the good and bad things, and what you can use this knowledge, yes? Because maybe bad people learn to you something, you say, oh, maybe this way is wrong to me, yes? And you can do something different. My travel was in this idea, really. It wasn't like a tourist travel. For that, yes, I was in a lot of beach. I was in a lot of, all kind, desert, jungle, forest, yes, mountain, lakes. But after 4 years, one lakes more or less is really the same. Yes, the most beautiful is the people that where you are. Yes. Okay. Another. Just tell me.
What were your biggest struggles during your journey?
Troubles?
Yeah.
Well, yes, in the beginning was because I started my travel with a budget of $2 in a day, yes? And in the beginning was this the problem. And really I was scared when I started for where I can spend the night, the food. But then you can learn to trust in the life, because it's something nice that if you have the discipline, yes, and you put your goals, and then you work in your goals, then the life make the rest, yes, because it's impossible to control everything. Your mind is limited. The life is infinite, yes, and for that you have to make like put in your life like a goal, and then let the life give you the stuff that you need to get your goal. In this way, for example, the problems, the troubles that I had become to appear in different way, because it started to appear to me like a challenge, yes? And when was really big, the problem was a big challenge too, yes? And people wrote me in a country, in one country, I have problem with, with the weather, with roads, a lot of problems, But I'm saying thank you at this kind of troubles. Why? Because it was challenge. And what kind of challenge? A challenge that I choose. Yes, and for that, if the travel was easy, I don't need to do that. Yes, because why? I don't need. If the university was easy, if you know everything that you try to learn here, what are you? Why you are here? You understand? And for that, when I was thinking in my travel, I thought, oh, I hope that the travel was a really big challenge. If not, I am losing the time. Yes, I think, but then it's something weird, because then the biggest problem or trouble maybe was miss my family, my friends. Yes, the time that because we are, social animals, or we are social animals really. Maybe I miss that, no? My I don't know, my people, yes, but no, maybe no, the food that I eat in Argentina, or this kind of stuff. Really, make a hack, yes, this kind of stuff. This is outside of the knowledge. Yes. Okay, now welcome. Another? Yes, sir. Well, it's nice because it's a mountain bike, yes, but I fixed to ride on the road. And this bike was my favorite bike when I was 15 years old. When I got my first job with my first salary, I went to the bike store, and I could not find it because it was old, and I have to wait in the newspaper that appeared, but really something like Amazon in Argentina, and I buy the maybe 10 years later. Yes. The cost, $100. Yes. Yes. Maybe you have the best bike in the world, but the motor always in the bike is you. If you have the will to move the bike. Yes. Whatever was that. Okay. Sorry. A ver, un poquito la... Okay, yes, it's really hard, yes. No, thank you, it's the first time that made me this kind of question. Yeah, gracias, Sonia. In the beginning was really hard, and I was shy when people ask me, I feel fault. Well, for two things. In the beginning, because I was traveling really with few money, no? And then I say, I said, oh, I'm riding my bike. The life is beautiful, and why everybody cannot do that? Yes, it was crazy. For that, when somebody tried to help me, I said all the time, no, really, I don't need your help because I'm okay, because I feel that my life, that I had more than I really merecía. Oh, thank you. Okay, but then. My idea changed. Why? Because I feel that I was cutting some energy, the energy of the life. Yes, because if you see the sailor, no, in the ships, they use the wind to travel, and I start to feel this kind of help in this way. It's like a wind. Yes, and in the video, in some moment appeared that I am with the postcard, and this way I found this idea because I was selling a postcard to finance my travel. But my postcard doesn't have price, yes? it was only for donation, yes, like donation. And sometimes people give me only $1, and sometimes $200. Yes, and if I put the price, maybe somebody want to help me, yes, and maybe the price is too much expensive, yes, but maybe some people can help me with more money, but say, oh no, maybe it's $5. You're $5. I close the possibility that the life surprised me, yes. I told you too that to me, my travel was, I was happy to do my travel. I was like full, yes, my spirit was full. For that, all kind of help is welcome, yes, because help me to get my goal. And in this way, the life is beautiful. Not welcome, yes. Another, please.
We are coming into the time for the next speaker, but thank you so much.
Oh, well, thank you. Thank you for inviting me.
Professor Cominsky founded the Education and Public Outreach Group at Sonoma State University in 1999 and is the project director, principal investigator on over 17 million in grants and final technical review for all products. She is also co-principal investigator on additional 5 million in federal grants. The mission of SSU EPO group is to develop exciting formal and informal educational material to inspire students in grade 5 to 14 to pursue STEM career, to train teachers nationwide in classroom and for the use of materials and to enhance science literacy for the general public. For decades, Professor Cominsky has been a leader of various different outreach efforts spearheaded by the Educational and Public Outreach Program. These include the outreach for NASA-funded program, the Fermi Gamma Ray Space Telescope mission, for the outreach effort for the U.S. portion of the European Space Agency XMM Newton satellite in 2003, to name only a few of the prestigious projects that Dr. Cominsky was involved in. Starting in 2013 and in partnership with SSU's early academia outreach program, Dr. Cominsky's group developed a 2-year high school curriculum called Learning by Making. This 5-year project is currently being piloted with 6 high-need rural high schools in Mendocino County. The group also developed an online course to educate lower division physics instructors about the science of LIGO and plans to pilot a second course about LIGO technology. Professor Cominsky has been a member of many different prestigious and important advisory committees and a recipient of many awards. I won't read the award because I want to hear the talk. But nevertheless, the title for today's talk is The Science of War and Peace. Please welcome Professor Lyn Cominsky.
I've been giving this talk for a few years now, and you might wonder, after hearing the description of all the work that I'm really working on, which is mostly training teachers and training students to do electronics and programming and physics, and mostly with an environmental type slant. Why is this my hobby, talking to people about nuclear weapons? And it all started back when I was a graduate student. My PhD thesis work was all about thermonuclear explosions on the surfaces of neutron stars, which are collapsed cores of stars out there in the cosmos. And it turns out that the very same processes that work in the stars are what they use to make the different kinds of bombs. And for a little while, when I was finishing my postdoc at UC Berkeley after I moved to California, and this is back in, it's really a long time ago now, I'm going to feel really old, the early 80s, and this was the time when Reagan was president, and they were doing this thing called Star Wars, otherwise known as Strategic Defense Initiative. I was looking for jobs, what to do after I did my first postdoc, and I interviewed at the Lawrence Livermore National Laboratory. And because of the work that I had done in my thesis on, I had learned a lot of the physics about weapons, and so I got some extremely lucrative offers from the bomb building divisions at Livermore, but also the policy-making division. And so I decided that I would research, look into what it would be like to work on developing policy about strategic issues. And so I taught myself a lot of stuff about how bombs work and, what was going on with that. And I don't have any security clearance, so everything I'm going to tell you today is basically unclassified knowledge, because if I had a security clearance, I wouldn't actually be able to give this talk. Interesting irony there. So you can find most of this information on the internet, just like I did. Of course, I can tell whether it's reliable information or not, but it's been, needless to say, I did not take that job. I ended up staying at Berkeley, running a satellite project, and then eventually coming to Sonoma State in 1986 after the space shuttle blew up and the satellite I was working on got delayed a whole bunch. It was like this cosmic sign, change careers now. Okay, so I've been here, this is like my 31st year, and this may be, I don't know, the 20th time I've given some version of this talk. It's been renamed from Physics of Nuclear Weapons or Physics of Weapons of Mass Destruction to The Science of War and Peace, to make it seem a little friendlier. We'll see how well that does. So what I'm going to talk to you about today is mostly the physics of how the different kinds of weapons work, and then some stuff about the spread of weapons around the globe. And every year I think, what am I worried about the most? What's going on in current events that's what I'm worried about the most? For the past couple years, it's been Iran. But this year, North Korea wins again, so I'm going to tell you what's going on with North Korea. A few years before it was Iran, it was North Korea. Then it was Iran for a few years. Now I'm back to talking about North Korea. So we'll get started here. Okay, so science. It's a sort of a value-neutral thing, right? And the good thing about science is that it's true whether or not you believe in it. Like one of my favorite quotes from Neil deGrasse Tyson, who is somebody I've known for over 30 years and stars in a lot of TV shows and is quite a famous guy now. And here's also an interesting quote from J. Robert Oppenheimer, basically talking about what motivates scientists, right? So you see something, it's just really appealing in a technical sense, and so you decide to go ahead and figure out how that works, and later you worry about whether it's a good or a bad thing, right? So the value judgment comes in when you start to apply the science that you figured out to a specific thing. Science doesn't really care what you apply it to, right? The science is still true. So if you look at the different fields of science and you look at, a certain technology, there's war versions of it and, there's peace versions of it, right? And it's really just the same science. So in chemistry, good uses of chemistry are pharmaceuticals. Bad uses of chemistry are chemical weapons, for example. The subject of this talk is really more about, nuclear power and nuclear weapons, right? The two sides. Nuclear power could be argued that it's a good thing. It's carbon neutral. Of course, there's that waste problem. I'm not going to really have a lot of time to talk about nuclear waste disposal or nuclear power. That's like a whole other talk. But if you look at all the different things, all the different components, you can see there's two sides to every coin as you go down the different fields of science. Okay, so some history. Just so happens that around the time of World War II, physicists were figuring out how atoms worked, the internal parts of the atoms, what they were, how they worked, where the energy came from, what held the atoms together, how to break the atoms apart. And they figured out that it was possible to release huge amounts of energy by breaking apart the atoms or smashing together some atoms. That's fission and fusion. That's far more energy than can be released in a chemical reaction. which doesn't break apart atoms, it just moves electrons around. So what would Einstein do? Well, in 1939, most of the prominent Jewish physicists from Europe had left for obvious reasons and had resettled in the US, including Einstein. And he realized that the inner workings of the atom that the physicists were figuring out could have this terrible potential of being able to be turned into weapons. And so he wrote to President Roosevelt and alerted him about that. And they basically said, oh, okay, ho-hum, you scientists, you just go off in your corner and do stuff. And it wasn't until Pearl Harbor that they took it seriously and decided, oh, we better figure out what's going on here and capitalize on making weapons from nuclear reactions before anybody else, namely the Germans and the Japanese, beat us to it. So after 1941, the US began to have this race with Nazi Germany to develop the nuclear weapons. And I think you've already seen the film The Day After Trinity by now in this class. You haven't actually seen it yet? Okay, so this might be news to you. Usually I'm right after the movie. Okay, so the government funded something called the Manhattan Project, which was actually in Los Alamos, New Mexico, not in Manhattan. And most of the funding went into make these factories that could produce the actual specialized materials that you would need to make the bombs out of. And then the first successful test was called Trinity, and it happened in 1945 in a test range near Los Alamos called Alamogordo. Everybody with me so far? We're doing good? Okay, here comes the more sciencey part. All right, so nuclear physics versus chemistry. This is a little cartoon of an atom. These are the electrons. There's 2 protons and there's 2 neutrons. They're in the nucleus. So if you're doing chemistry, what you're doing is you're moving these electrons around and putting them on other nuclei from other atoms. But if you're doing nuclear physics, what you're doing is breaking apart the nucleus, or changing protons into neutrons plus electrons, or changing neutrons into protons plus electrons, and a bunch of other particles. And if you're doing chemistry, the typical energies are measured in electron volts, where if you think of your 1.5 volt AA battery, that has enough energy to move 1 electron through a potential of 1 volt. And if you've ever played with batteries, you know that isn't a whole lot of energy. You can't really shock yourself or hurt yourself very much by short-circuiting the battery with, say, your body parts. On the other hand, with nuclear physics, if you're going to change the way the constituents of the nucleus are arranged, then the typical energies involved are millions of electron volts. So as you can see, that would be millions of times more energy than you get in chemistry. Now, this particular atom is a helium atom, and so it's got the number 4, which is the count of what's in the nucleus, 2 protons plus 2 neutrons. And because there are 2 protons, which have the positive charge, there's also 2 electrons. So that's just normal inert gas helium. It's the second element in the periodic table for those of you who remember some chemistry. Now, if we're going to build bombs, what we need to do is we need to manufacture some sort of specialized materials. So here's a chunk of uranium. It's only 1 inch long and it weighs 10 grams. Okay, fairly dense stuff. Normally, if you find some uranium in a rock in the ground, 99% of it is going to be this isotope of uranium called 238, which means that the sum of the neutrons and the protons in the nucleus equals 238. Since uranium, the definition of an element is how many protons it has. Uranium has 92. That means if you add that up, you get 146 neutrons. On the other hand, if you actually want to make a bomb, what you need is a different isotope of uranium, and I've put the dangerous things in red. So you need a version of uranium that only weighs 235, so it's missing 3 of those neutrons. That's less than 1% of what's going to occur naturally in that rock in the ground that you're mining out of the uranium mines. So if you want, here's some of that. So if you want to make a bomb, you have to do what's called enriching the uranium so that you enrich the percentage of 235 versus how much 238 you have. That makes sense to everybody? Okay. So for a fission weapon, then what happens is you have this uranium-235, you shoot neutrons at it, it fizzes, blows up, breaks apart, you get all these different pieces come out, different sizes and shapes of elements, you get a bunch more neutrons come out, and if you can take these neutrons and stick them back in to what's left over of the uranium-235, you make a chain reaction that's self-sustaining until the whole thing just blows all up. Okay? So that's a fission reaction, and that's what happens with atomic bombs, or A-bombs. That was the first kind that they figured out how to make. That was what was the nature of the Trinity test. And so that's fission, because it's splitting up. And you could also, besides using uranium-235, you could use plutonium. Now, plutonium, which weighs 239, doesn't occur in nature naturally. It's normally radioactive with a fairly short half-life, so any plutonium that was made when the Earth was created has long since decayed away to other things. But you can make plutonium in reactors and then use that to make parts of bombs. Okay, so the first A-bombs, the first one was Trinity, as I mentioned before. That had the equivalent yield of 20,000 tons of chemical explosive. That's the kind of stuff that you normally call, TNT or dynamite. So when you do this equivalent yield, it's like, how much dynamite would it have taken to make the explosion that they saw? And Little Boy and Fat Man, which I'll talk a bit more about. And so this Little Boy is the weapon that was dropped in Hiroshima. Fat Man was dropped in Nagasaki. Also similar yields, only like a month later, less than a month later. Each one of these weapons consumed the equivalent of about 2 pounds of fissile material. So uranium-235 or, its equivalent. They were both uranium in this case. Okay, so rather than having 15,000 pounds of dynamite, it just took like 2 pounds, which is about the size of a baseball, of uranium to make the equivalent huge explosion. That's called the efficiency of a bomb. How much fissile material it takes to make how big of an explosion. Okay, so how do you make an A-bomb? Now this is the physics, this is not the engineering. I'm not an engineer. I don't actually know how they construct them. I just know the principles, the physical principles behind how you do it. So you have to enrich the fraction of uranium-235 to be more than 90%. Now remember, it just starts out to be 1% in nature, less than 1%. So you've got to go through this enrichment process so that you get rid of most of the 238 and all you're left with is the 235. Then you have to squeeze it and confine it really evenly so that you can catch the neutrons that come out from the initial reactions and send them back in. And it takes a bomb to make a bomb. So you start the whole thing off with a chemical explosive, and then that's called the trigger. Now, Little Boy, the weapon that was dropped in Hiroshima, it was a so-called gun-style device. So you had a chunk of uranium-235 here, another chunk here. You lit off the gunpowder or the dynamite, and you smash these two together. At the same time, you hit it with a blast of neutrons. You've got the critical mass of uranium. The neutrons start doing their thing. This protective shell on the outside, which is usually called the tamper, catches the neutrons that come out, puts it back in, and in 1 microsecond, a millionth of a second, it's all over and the whole thing is totally blown up. Okay, so all of that action of catching the neutrons, sending them back in, continuing the chain reactions very, very fast. That outside of the missile casing, it can only hold it together for a little while. Now for Fat Man, they did a different style. They did the same style they did for Trinity, which is the spherical one. So in the inside, they put the uranium-235, and the outside, they put the chemical explosive. They had lenses to make sure that it got all squeezed and compressed very evenly around the whole big spherical ball. At the very center, there was a little burst of a little neutron generator, usually made out of beryllium and polonium. So when that got squished, it let off a burst of neutrons. Then this stuff is at critical density because it got squished by the explosion all around it, and that starts the chain reaction. So they're sort of a cartoony version. Okay, any questions about either one of those so far? Are we doing good? You might not have thought much about this. Okay, so fusion weapons. So if you have elements that are heavy like uranium or plutonium, the way you get the nuclear energy out is you break them up. But if you have really lightweight elements like deuterium, tritium, and lithium, deuterium and tritium are both forms of hydrogen, then you have to squish them together to make the energy come out. Now that's sort of challenging because these elements have positive charges in the nuclei, and you may know that opposite charges attract and like charges repel. So if you're trying to squish a bunch of positive charges together, they're going to push back. So you have to figure out a way to get them to get together to get to this high enough density that the fusion reactions will ignite. Now our sun has no problem doing that. Okay, that is what goes on in the center of our sun that makes the sunshine. Okay, it's been doing it for 5 billion years. It's got about another 5 billion years to go before it runs out of fuel. And that is what makes H-bombs or hydrogen bombs. Okay, so here's two deuteriums. You squeeze them together. They're each hydrogen with an extra neutron in them. You end up getting helium when you do that. Or you could do, and so deuterium is often called heavy hydrogen. Tritium is like super heavy hydrogen. It's like 1 proton and 2 neutrons and 1 electron. Deuterium is 1 proton and 1 neutron and 1 electron. Normal hydrogen has no neutrons. It just has the proton and the electron. And moreover, these reactions, these fusion reactions, are thermonuclear. And what that means is the hotter you have the situation, the more quickly the reactions proceed. And then that makes more heat, and then the reactions go even faster. And so it's a very efficient process for making an explosion. Okay, now the nice thing is that when you're done with the fusion reaction, mostly what you have left over is stuff like helium, which is a pretty benign substance compared to all of the random fission fragments that you get out of blowing up uranium, which leaves behind lots of other randomly radioactive things. So obviously, since the A-bombs worked, they went on to see if they could make the H-bombs work, and yes, they did, but then we've never actually, other than testing them, we've never actually dropped one on anybody, which is a good thing. So why is an atomic bomb so much worse than a chemical or, TNT kind of bomb? Well, because of the differences in the energy of electrons versus nuclear processes, the amount of heat and light energy that you get out is about 1,000 times greater. Plus, unlike the chemical reactions, when you make this explosion, you get all this penetrating harmful radiation. You get alpha particles, which are helium nuclei. You get beta particles, which are high-speed electrons. You get gamma rays, which are not mass at all, but the highest energy form of light. And after the explosion, those radiation particles and any fission fragments that have come out from blowing up the uranium, they stick to stuff like dust or water molecules, and then they go up and they spread, and then they fall down, and that's what the fallout is, as you probably heard about. So you get all this radioactive stuff coming down from the sky after the explosion. That does not happen with a chemical weapon. You just have more chemicals left over. So this is I'm going to show this little movie of Trinity, and hopefully it'll work. So the mushroom cloud and the fireball. So what's that all about? First, let me attempt to show this. Let me even attempt to make noise. Maybe not so much noise. I don't think they have the volume turned up. Well, forget the noise. Okay, so you get this big ball of hot gas, and as you know, heat rises, right? So there it is. It's this big ball of hot gas. It's rising up. Well, as the hot gas rises up, the air that used to be down here, it's like a vacuum. And so it sucks up, like a vacuum cleaner, it sucks all the stuff underneath it up in the mushroom stem, right? All that dust and dirt, or if you did it over water, it could have been water, right? And then that stuff goes up and joins the big fireball. And then as the hot ball of gas that's now got all this radioactive dust and dirt in it goes further up in the atmosphere, it eventually gets to the place in the atmosphere where the pressure of the atmosphere, which is less as you go further up, you probably noticed that if you've ever gone mountain climbing, it gets to the place in the atmosphere where the pressure inside the hot ball of gas is the same as the pressure of the atmosphere, so then it spreads out, right? And that makes the mushroom top, right, that you've heard about from the mushroom cloud, right? So it just starts out as a big ball and then spreads out. Before it gets to the place in the atmosphere where the pressures are equal, the atmosphere is pushing on it and just keeping it in the ball shape. Does that make sense to everybody? Okay. So this is this fireball. Now that big ball of hot gas, I'll play it again. That big ball of hot gas, there it is. See, it's like a ball shape. Here comes the vacuum action, sucking up the stuff up the mushroom stem. This ball of hot gas is millions of degrees temperature, okay? Anything that's anywhere near it is just going to get incinerated. It also makes all this radiation that I told you about, and it sends out a huge pressure wave because now there's this big ball of hot gas. There used to just be plain old air. Sends out a huge pressure wave, and the pressure wave can knock stuff over. Okay, so then buildings fall down and things like that. Okay, any questions about any of those processes? Okay, so we've got our buildings collapsing from the pressure wave, and then we've got all of these radioactive fragments that are sucked up the mushroom stem that spread out on the top of the mushroom and then come down like all different places. 80% falls back down in the first day, 90% in the first week, but the other 10% gets up to the part of the atmosphere that circulates around the whole globe, and it just keeps going around and around for years. There's still stuff up there from the nuclear tests that we did in the 60s that were the tests that were atmospheric. It's still falling down, even all these years later. Try this. If you want to see, like, plug in the size of a weapon and see how much would get incinerated on your favorite city, like San Francisco, you can give it a try. It's a sort of an interesting thing. It probably still works. I didn't try it this year. Usually I try it every year to make sure it still works. Okay, and now there's one more weird thing that happens, which is called the electromagnetic pulse. So if you have an explosion that happens really far up in the atmosphere, it's much stronger. And these gamma rays, these high energy forms of light that are part of the explosion, they ionize the air molecules. Okay, now normally air is not that great of a conductor, although I'm sure you've all had the experience of, shuffling your feet on a rug and going up to a doorknob and getting that shock, right? That's actually electrostatic breakdown of the air, that shock. It's a low voltage, so it stings, but it doesn't kill you or anything. But if you take this to the extreme, when you ionize the air, you can get a current flowing through it, and that's basically what's happening when you shock the doorknob or your car door handle or whatever it is, right? That's just you're ionizing that little tiny bit of air between your hand and the doorknob, and a current is flowing. That's what you feel is the shock. But if you have something that's this powerful, you're going to ionize a whole lot of the atmosphere. So current can now flow through the air, whereas normally it does not. And then these currents that are flowing through the air, they get picked up by the power lines. You may have had the experience of hiking under a high voltage power line and like hearing a crackling, or maybe feeling like it was doing stuff to your hair or something, right? There's a little bit of ionization going on in the air near those high voltage power lines. But these power lines, or any electronic device, will pick up these currents, and the power surges will go down the line, shut down the grid, and destroy anything that's attached. So pretty much say goodbye to your computers, your cell phones, you know, all your household electrical devices, the entire grid. It's really very effective. For example, they had a 1.4 megaton, so that's millions of tons equivalent, airburst in 1962 that was just an atmospheric test. They weren't trying to kill anybody. And it killed all the power in Hawaii 1,000 miles away. Knocked out all the lights. This next slide is a little map that just sort of shows. It would basically just take one really high burst at about 300 miles up, nice strong bomb, and wipe out the entire grid for all of the US, just one bomb, if it was strong enough and high enough up. Pretty scary to think about that, because nuclear weapons really are scary. I think the reason, you know, they have the rep that they do is because most of these terrible effects are due to the radiation, and so you can't smell it, you can't see it, right? All of these particles are invisible and penetrating, and unless you happen to carry a Geiger counter around in your pocket, you're not going to know that you're near something that's radioactive or that has these particles that could hurt you. If you're exposed to a lot of radiation, it takes 20 or so years, if you don't die right away, it takes 20 or so years for the cancers to develop that came from the mutations in your cells that were affected by the radiation. In the case of Hiroshima and Nagasaki, it just took one bomb to destroy an entire city and kill 100,000 people like that. And it only takes a couple pounds of this stuff, this uranium, to make this big explosion. It did, however, take a lot of complicated engineering to really make that work, which is why, in general, you know, individual scientists don't do this. This is the kind of thing that is developed by an entire country that's putting lots and lots of resources into creating the entire infrastructure to manufacture the material, enrich the material, shape the material, get all the electronics, get the delivery systems, and all the other parts that you need to make the bomb. So how big are these? Well, I mentioned that 1 kiloton is like 1,000 tons. A ton is 2,000 pounds. So that's 2 million pounds of TNT equivalent, and it just takes 2 pounds of uranium-235 to make a 20 kiloton weapon. I mean, think how much room it would take to have 2 million pounds of dynamite, right? That's really a lot of physical space compared to something that's the size of a baseball. The typical warheads on the weapons that are in our stockpile are 100 to 200 kilotons. They're 10 times at least more energy per bomb than what we dropped on Hiroshima and Nagasaki. When we were doing testing in this country, the largest underground burst was 4.5 million tons. The largest air burst was 58 million tons. And there were over 1,700 tests that were done by the countries that were developing these weapons since 1945, when this all started. Okay, that's sort of the end of the war part. Any questions about the weapons? Yes, sir.
For the largest airburst, wasn't that the Zahra test from the Soviets?
Yes, it was from the Soviets. I don't remember the name of it offhand, but it was a Soviet one.
How feasible is it to make to miniaturize? Like, do we have the technology to miniaturize it and make it feasible now?
Not a burst that big, but as I just showed you from that EMP thing, you don't actually need to have things that are anywhere near this big, right? So people just wanted to see what they could do, impress the other countries, right? But
Because I remember in one class we were learning that they wanted to do
And they might want to do that, but most of the weapons that can be carried on regular sized missiles are like the 100 to 200 kiloton ones. And then what you have is you have the cluster, right? You have the MIRV, multiple reentry vehicles. So you've got 10 100 kiloton warheads on one rocket, basically, right? So then that's like, 1 megaton. Okay, so Atoms for Peace was started by President Eisenhower in 1953 because everybody was so horrified about what happened in Japan, and the war was over and we won, that we wanted to find a way to turn the weapons into something that could be useful, like nuclear power plants. And so the US went around and helped countries that said that they would only use peaceful uses of nuclear weapons to build nuclear reactors in their countries. And one of those countries was Iran, who was our friend back then in the 1950s. People that were in charge were put there by the US government. So what is it that we've actually helped them do? Well, first of all, you've got to get the uranium out of the rocks in the ground. So you make a mine, you get this ore that comes up from these mines. A lot of times to get the uranium ore out of the rocks in the ground, you put this nasty extracting solutions, they're mostly acids, on the rocks that creates a bunch of nasty chemical waste leaving behind. Then you crush the ore, you extract the uraniums from the ore, the 235 if you can, and you leave behind all the rest of the rocks, which are usually a little bit radioactive, and they just sit there by the mine. And by the way, most of the mines in this country are in places that are Native American reservations. So we've left a lot of garbage behind in these places when we're done doing the mining. So then you extract the uranium with more acid and you make this stuff called yellow cake, which is compressing it into a powder. And then you turn the yellow cake into uranium hexafluoride gas, which you can cool to a solid for easier transport. So this is all the steps of uranium processing. And we haven't gotten to the enrichment part yet. So to do the enrichment, there's lots of different ways to do it. As I said before, to actually make the material for a weapon, you need 90% or more of this isotope of uranium. That's the number 235. That's called highly enriched uranium. If you stop your enrichment when you get up to about 5%, that's what's used in nuclear power plants. It's called low enriched uranium. There's a long way to go between 5% and 90%. Lots of steps of enriching. And there's lots of different ways to do the enriching. Because I'm not really focused on Iran that much for this talk, I'm not going to go into detail about the gas centrifuges, but I can certainly show you slides about that if you're interested. So that's what Iran uses, and that's what, after the first Gulf War, were discovered these gas centrifuge plants in Iraq. But basically, if a centrifuge is you're spinning stuff around, the heavier stuff gets flung to the outside. So if you've got uranium-238 and uranium-235 and they're both gas, the uranium-238 will move to the outside. They get rid of it. They keep the stuff that stays in the middle. They send it to the next stage of the centrifuge. It takes thousands of stages of centrifuges to get any quantities of the uranium-235 that's the highly enriched, greater than 90% kind that you want. Thousands and thousands of these centrifuges. Another way is gaseous diffusion. That's what we use in this country. That works on the fact that the different isotopes will, if they're gas, will travel at different speeds. The lighter one can go faster than the heavier one. So you send it through a filter and you get the lighter stuff out, and then you send it through another filter and you get the lighter stuff out, and eventually you purify it that way. Now this one is weird, electromagnetic isotope separation. We didn't think anybody would do it this way. It basically just uses an electric field that operates on the isotopes and separates them out by using lots and lots of electric power. And when we finished the first Gulf War, which is the one about Kuwait, for those of you who don't remember or haven't learned it, we found all of these underground processing plants that use this method. And the reason we never thought anybody would do it is because it just takes so much energy to make these strong electric fields to separate these things out. But you know what? Iraq had all this oil, so they had no problem making lots of electricity to make the big electric field to separate them out. We wouldn't have done it because we could do it in a more efficient way that used less power. But for them, it was no problem. So that was a big surprise. The fact that we found these enrichment plans underground that we didn't even know about until after that war was one of the reasons that people, politicians like George Bush, thought that for the second war that they really had something they were hiding and that they were still doing things in tunnels. I mean, it was one of the reasons it was plausible, even though, of course, later it turned out to be totally a lie. But it was plausible at the time because we had this experience of finding these secret enrichment plants after the First War. Okay, so there is a treaty called the Non-Proliferation Treaty, and every 5 years they have a meeting of all the people that have signed it to make them re-sign. So it's 2015 was the last time they had the meeting, so the next one will be 2020. And this map just shows like who's signed the treaty and who hasn't signed the treaty. So first of all, there's the big five, the states that are the have states, the states that are acknowledged developers of nuclear weapons. So the US, Britain, France, Russia, China. Did I miss one? No, that's 5. Okay. Then all of the green states, all of the green countries have signed the treaty, and what they've said is, we won't build any. We agree not to build any, and you can inspect anything that we want. Then there are states that haven't signed, like India, Pakistan. Then there are states that had signed originally, like North Korea, and then quit. So that's a withdrawn. Oh, Israel also never signed. What am I missing here? Well, anyway, that's pretty much the status of the treaty for now. And then they vote to extend it for another 5 years. Oops, I should have changed that to 2015. Okay, so like for example, North Korea signed it in 1985, then it withdrew in 2003, and then in 2006 and 2009 it started testing because it was no longer bound by the treaty that forbids you to have testing. Israel, India, and Pakistan still have not signed and will not sign. But in the meanwhile, the reason I'm not so worried about Iran anymore is because of the Iran nuclear accord deal that President Obama got signed and ratified by our Congress in 2015. And as of January 2016, the International Atomic Energy Agency, that's in charge of checking all the countries and checking all their stockpiles and making sure that they're doing what they're saying they're going to do, they confirmed that Iran is abiding by the agreement that keeps them from being able to develop a weapon within about a 3-month time scale, which was the situation before the Iran nuclear accords were signed. The breakout time, which is what they call how long it's going to take them to make a weapon if all of a sudden they started cheating on the treaty, is now, more like years, not just a few months. So that's made everybody feel a little bit better. Meanwhile, North Korea has gone slightly crazy with its new leader, and it's just testing stuff and building missiles. So the first test that they had was in 2006. It was only about a half a kiloton. It was really even hard to tell apart from an earthquake, except for you could tell it was coming from there. It's believed that they have enough weapons-grade plutonium to make between 5 and 15 bombs. And it's probably more by now. So the plutonium gets created in nuclear power plants as a waste product. Okay, so if you have the low-enriched uranium and you burn that in the nuclear power plant, you make a bunch of stuff, one of which is plutonium. you can then recycle that plutonium out of the waste products and use it to make the fissile material that you need for an A-bomb. Then they started trying to make delivery systems. So in 2009, they launched their first long-range missile, but it didn't work. They had another underground nuclear test, which actually got their yield up to 15,000 tons. And then they were able to actually make fusion in the testing facility in 2010. And here's the new leader now, is taken over in 2012. He said, okay, we need food. All the people are starving. We'll stop testing. Give us food. And so they suspended it for like 4 months. Then in 2012, they tried to launch a satellite, which takes a long-range missile to do it, but the rocket didn't exploded, and then we suspended the food aid because they were already cheating after only 4 months. Then the next month, they started to make a new reactor building that could be used to reprocess that fuel and to get more plutonium out of the waste products of the nuclear power plant. And then they decided to go into the satellite launching business. So in 2012 and in February of this year, they managed to launch satellites into Earth orbit. So that takes a long-range missile to escape the Earth's gravity. They claim most recently they're working on a lunar program. I don't think anybody actually believes that. The 2012 satellite did not work. It tumbled and never communicated. And it's not clear that the satellite from this year actually worked, because no one's been able to intercept any actual communications with it. But at least it's not tumbling. It is in a proper orbit. So now they've spent 3 years upgrading their launch site. This is a picture of the 2016 launch. So the satellite is in a proper orbit. Now a polar orbit, because the Earth is spinning and the satellite's going like this, a polar orbiting satellite goes over every single spot on the Earth at least once a day. Okay, so that means they're going over us some of the time. If you're in an equatorial orbit that goes over the equator, you just go over the equator, right? But if you're in an orbit that's inclined, or a polar orbit, you go over all the different places on the Earth. So that's worrisome. And the 2016 satellite launch is a clear violation of UN resolutions that ban the country from carrying out long-range missile tests. Now, even more worrisome is that in August of this year, so, last month, they actually did here it is, picture of it, their first successful launch of a submarine-based missile with a range of about 1,200 kilometers. Okay, so that's a smaller missile that you put on the submarine, and the submarine can go over next to the country you're trying to bomb, and then you launch the thing up out of the water, and you don't even have to be, you don't even have to have a long-range missile that could get all the way to the U.S. from Korea. You just need to have a submarine that can get over to the coast of the U.S. that you haven't seen and launch from when you get close enough. So submarine-launched ballistic missiles are much scarier. And now this picture right here is the larger rocket engine test that they just did this month that is making people worry that they're closer to deploying long-range missiles. And I updated these slides yesterday, and in this morning's paper, there was actually a little article about how they think that a couple of the top nuclear engineers from Iran were the ones that have gone to North Korea to teach them how to build better rocket engines. So this is like a really weird and awful coincidence. Meeting of the minds, whatever. The country of Iran is barred from doing these kinds of tests themselves, but that doesn't mean that individuals in Iran can't just go out and be hired away or something by other countries to spread the technology. In fact, a lot of people think that North Korea got the stuff from Pakistan in the first place. So there's a lot of weird international connections, and I'm not really an expert on the politics of all of that. So bottom line, are we in danger from North Korea at this very moment? Not quite. Okay, so they've got their working nuclear warhead, at least in a test facility in the ground. That's not the same as being able to launch it on a missile and get it to work remotely. They now appear to have a working long-range delivery system. That was not true the last time I spoke about North Korea, which was 3 years ago, in 2013. I was looking back at my notes. There's no evidence that they can actually remotely trigger bombs because their satellites aren't working that great. And if they were able to really talk to their satellites and really have the functioning electronics, I would be more worried about that, because just getting data from a satellite is not that hard compared to sending a complicated sequence of signals that will detonate a bomb in a particular place. And then, of course, they have to want to actually bomb us, but, you know, I don't have insight into the mind of Kim Jong-un. So I don't know. It's entirely possible that he wants to bomb another country. He, of course, would never claim that out loud. He's just saying they want to go to the moon. That's why they're developing long-range missiles. So, okay, well, that's sort of the end of the official part of the talk. Here is a bunch of other links you can go look at if you want to read more about these various things. I'm very fond of both of these websites because they just have a wealth of information about the countries, the politics, the state of the technology in the different countries, and things like that. So, yeah, and then I have, you know, plenty of time for questions, I think. I have no idea when this class is over, but I have some amount of time for questions. If you have questions, I'll be glad to answer them. So, yes, sir.
Do you think, I know you didn't cover it, but do you think, has anybody speculated that the satellites could be with
So could these satellites actually have like kinetic weaponry, like laser beams and stuff like that, or the actual just kind of kinetic kill vehicles where they just launch projectiles? There's no evidence that they know how to do that yet. And it's not a terribly effective way of doing anything unless you're just trying to take out another satellite. And actually, South Korea is building a satellite interceptor system that uses more like that kind of technology, but it's not expected to really start working until something like 2017. It's called THAAD. Yes. Yeah, well, there's lots of different ways to do it. None of them are as efficient as actually just blowing something up. Yeah, I mean, polar satellites are scary for the reason that they do go over every part of the Earth. But, you know, then in order to be able to use that, you'd have to tell it to do something at some particular time and place. That requires communications technology that we can probably jam, right? And that they haven't demonstrated that they can even just talk to a satellite normally. People may know that Sonoma State launched its own little satellite in 2013 called T-Logo Cube. It was about this big. We were able to talk to our satellite with a radio antenna that we built in the backyard at my ranch. We've since built a copy of that antenna. It's on the 3rd floor of the Student Center. If you go down to the end opposite Overlook, you can see it. It's right there. And we just got funding from NASA to build another little baby satellite. This one's about this big. It's going to do environmental measurements. It's called Edge Cube. And so you may have seen some articles about that on the Sonoma State website or other places. So, you know, even our students can build simple satellites in a low Earth orbit and talk to them at least for a little while with cheap parts. But that's not the same as being able to really command it to do anything fancy. Oh, the Non-Proliferation Treaty? Okay, so the question is, what were some of the reasons that the countries like Israel and India and Pakistan didn't want to sign the treaty? And the reason is they have their own weapons and they don't want to talk about it, right? So if they sign the treaty, then the International Atomic Energy Agency could go over and inspect all of their stuff. And if they don't sign the treaty, they can't get inspected, right? So if they have weapons, and Israel for sure has weapons, India used to have weapons. Pakistan for sure has weapons. India probably still has some. They've done successful tests that have been, verified by other countries. They don't want anybody knowing exactly how many weapons they have, what kinds of weapons they have, where they're storing them. So they just won't sign. So then no one can inspect them and find out. Okay, was the U.S. the party that wanted everyone to sign the Nuclear Non-Proliferation Treaty? It was one of the 5 countries that wanted everybody to sign it. So the idea was the have countries would keep what they have, and they would give peaceful uses of nuclear technology to the have-not countries. And the have-not countries would accept the nuclear power plants and promise not to make weapons. And the have countries would promise not to make more weapons or advanced generation of weapons. Have we actually kept our promise? Not so much. A long time ago, more lately. Okay, we have separate treaties with what used to be the Soviet Union and is now Russia that has lowered the number of weapons that each country has. So each country now has only about, I think I have it on one of my other slides. They only have like a few thousand weapons now per country instead of, this one here, okay. So they only have a couple thousand weapons per country instead of like more than 6,000 each. Okay, well, as I showed you how much damage even one weapon can do, a couple thousand is still pretty dramatically more than you would need to destroy the entire Earth. So, but it's a step in the right direction that, we're getting rid of them and we're getting, we're breaking them apart and we're recycling the stuff that used to be inside the weapons, which has especially been worrisome because with the breakup of the Soviet Union, a lot of those manufacturing plants and a lot of those weapons didn't stay in Russia. They ended up in countries that don't have a very large military to protect them, like Ukraine and countries like that, right? So then you're worried about how well are the stockpiles of this fissile materials being guarded in a country that doesn't have a huge standing military like Russia does. So it's still, it's still worrisome. Well, now it's sort of equal with Russia, but those two together, Right. It does solidify our place, absolutely. And then Russia, at least caught up, if not surpassed. And you all know that, Russia has much better heavy-duty rockets than we have now, right? Why is it that the U.S. astronauts that are going to the space station have to go in Russian rockets? Because the U.S. industry no longer makes the big heavy lifting Atlas rockets that we used to use. Now we're trying to have private companies take over taking the astronauts to the space station, right? So the private companies are going to try to develop these rockets that we used to actually have. And in the meanwhile, for all these years, we've been letting the astronauts go in the Russian rockets because we don't have a rocket big enough that's made in this country that can take them there, which is a very interesting turn of events. Right, so are the North Koreans really interested in the satellite program? Well, I'm not a psychologist, but I would say they're just trying to show that they can do stuff technically, and they're trying to show South Korea that they can do stuff, and Japan, who they're right next to, which doesn't have a nuclear program because of what happened to them in World War II. They sort of forswore that, although some Japanese now are saying we should develop our own military again. So, it's, that's politics. I'm a scientist, so you should ask a political science professor about that who probably understands more about the different countries than I do. Okay, so the question is, if you fire an intercontinental ballistic missile with a nuclear warhead, can we stop it from getting to us before it gets to us and blows up? And that was what Reagan's Star Wars program was all about, the Strategic Defense Initiative, which is its real name. And so the idea was, you know, they would launch it, we would see it coming, we would try to intercept it and blow it up. Okay, so, you know, can two BBs hit each other fired at a distance of like half an Earth away? Not that easily, but you can do other things like make a big explosion near it and then, you know, divert its path, or shoot laser beams at it and destroy its electronics, or any of these fanciful Star Wars kinds of things, which is why it was called Star Wars. And so when I was thinking about taking that job, you know, long ago in the policy division, you know, I knew that what they were going to ask me to do was decide, well, you should do Star Wars this way versus this other way, right? Like calculate all these different scenarios of like what would work better. And most of the physicists that were studying the issue at the time just decided it was all really stupid and it was never going to work. So I decided I would not actually keep that job for very long. So it was a good thing I didn't actually go work there, although it took a long time before I made that amount of money. And they were offering me back then. So, but you know, life is choice, right? You gotta decide. And as you can see from my jewelry today, which side I'm on in the war versus peace discussions. Okay, so is it possible to create a cobalt-60 bomb? Now, usually most of the other elements that are radioactive like that, like stuff like cobalt that's used in medical things, those are usually called dirty bombs. And what they do is they don't make a nuclear explosion, they just spread nuclear waste everywhere. Then you've got this tremendous cleanup problem, right? So it's a different approach. It's like a weapon of mass terror instead of a weapon of mass destruction, because like all of a sudden you just spewed radioactive garbage over a whole area. And so that's a different problem than blowing down buildings, irradiating people, having firestorms, making electromagnetic pulses, and all that stuff that, you know, regular nuclear weapons do. I don't think that's really a hand, because I think that guy's actually looking at his cell phone back there, but he was like stretching while he was sleeping. Anyway, almost looked like a hand. He doesn't even know I'm talking about him. That's okay. Keep looking at your cell phone. Any more questions from anybody? Okay, so the question is, what is depleted uranium? So when you do the uranium enrichment process, the stuff that you had this, you know, 99% 238, less than 1% 235. Then you enrich it, so you end up with all this uranium 235. The stuff that's left over is almost all 238, even more so. It's called depleted because it was depleted of the 235. It's still a little bit radioactive. Normally uranium-238, just sitting in a rock in the ground, is radioactive. It just has a 10 billion year half-life, so it's not a really fast reaction. But it's still a little bit radioactive. But the stuff that's left over, uranium is this really, really dense metal, right? If this little ball is, you know, a little tiny ball weighs, you know, several pounds. So what they were doing was they were making the outsides of the missiles, the so-called tampers, they were making it out of the 238 and the depleted stuff that was left over. Well, that seems like a good use for it. The problem is that in the first Gulf War, we also started making tank bodies out of it. And our soldiers were sitting inside the tanks, right? And then the tanks were radioactive that they were sitting in. And then we just left all these tanks over there after we got out of Kuwait. You can see pictures of it online. And there have been a lot of health effects that have been associated with it that we exposed our own soldiers to because they were sitting in these very dense, thick, protective tanks that unfortunately happened to be irradiating them. So I don't think they're doing that anymore. At least I hope they're not. That was not such a great idea.
And also, I have a question about the way that we store atomic bomb in this country. And does atomic bomb have the expiration date, or will they install it?
Okay, so the question is, Yeah,
Yeah.
so the question is about the stockpile of the atomic weapons and how do we know whether the weapons are still going to work and like do they just, have some expiration date and then they stop working? That's actually a really good question. And the way we used to check on the stockpile and whether we thought the bombs would still work was we'd blow one up every once in a while and see if it still worked. But we haven't actually done any underground testing in this country now since the days of Bill Clinton. He stopped it. And so that was a number of presidencies ago. And so now what they're doing is they're doing stockpile management by simulating what's happening with the stockpile with fancy computer programs at places like Lawrence Livermore. And, they're trying to verify the condition of the stockpile and they do all these runs and they do some tests, but they're not actually blowing up anything to see whether the stuff really still works. Just a different approach that doesn't make any more bomb explosions underground. And of course, atmospheric testing was stopped in the 60s, which is good. Once they realized how much stuff was staying up there in the atmosphere and that it was continuing to circulate, radioactive particles. Okay, well, I thank you all for your attention.